Hello, this is my presentation for the project of the course Computational Photography, and my name is Prakanshul Saxena. The topic of the project is fast separation of direct and global components of a scene using high-frequency illumination. First, let's see what are the direct and global illumination components of the scene. The radiance of a surface point measured by the camera pixel due to a significant scattering event is referred to as the direct component of the scene. The remaining radiance measured by the camera pixel is referred to as the global component. In addition to the interreflections, the global illumination received by the camera pixel may be due to subsurface scattering, volumetric scattering, or even light diffusion due to translucent surfaces. Now, moving forward, the separation of direct and global components of measured radiance is useful as those components convey very different properties of the scene. Direct and global components at all scene points can be measured using high-frequency illumination. When a light source radiates a high-frequency illumination pattern, the lit patches include both direct and global components of the scene. All the unlit patches only have a global component. We denote the radiance of the patch I measured by the camera C as LCI, and its two components as LD, the direct illumination, and LG, the global illumination. Lij is the radiance of the patch J in the direction of patch I, and Aij incorporates the BRDF of I, as well as the geometric configuration of the two patches. We further decompose Lg into two components as LGD and LGG, where LGD is due to the direct component of the radiance from all scene patches and LGG is due to the global component of the radiance from all scene patches. Now, when we assume that only a fraction alpha of the source pixels are activated and that these activated pixels are well distributed over the entire scene to produce a high frequency illumination pattern, the previous equations change accordingly, where Q is the set of illuminated patches and the function lit indicates whether the patch is illuminated or not. Now, if we also assume that the brightness of a deactivated source element is a fraction b of an activated element where b is between 0 and 1, then the previous equations are modified as seen. If alpha is either close to 1 or 0, the scene will be lit very sparsely in one of the two images. Since we wish to maximize the sampling frequency of the illumination in both images, a good choice for alpha is 1/2. Lmax and Lmin are maximum and minimum camera pixel values. Now this is the setup for the capturing of the illumination patterns in which you can see the projection of the checkerboard pattern and the illumination and the screen, the blue screen, the object, and the camera. To further explain the setup in detail, a total of 25 images were captured per scene with a shift of 3 pixels for the pattern across the image. The pattern is a checkerboard pattern, and each square of the pattern consists of 8 cross 8 pixels. Now, these are the results on the direct and global. These are the results which show the direct and global illumination of the scene. The room was pretty dark, so the global component seems to be dark in that sense. Only light on the object was majorly of the projector. Now, in this result, we can see the approach fails in parts where the objects exhibit subsurface scattering and have high specular surfaces, such as the top of the bottle and this white plastic saucer. Now, this is an object I specifically a half-cut tennis ball and painted. I use this object to first obtain direct and global illumination components and also to obtain the results for the shape of the objects when measured using direct illumination image and the original image. Now here we can see the original image produces an incorrect shallow shape. The direct images result in a shape that is very close to the ground truth shape, which was manually estimated. Thank you for listening.